Today, Huang from UCLA, and he will talk about orthogonal Grassmanians and three-algebras. Thank you.
Thank you. Thank you very much for the invitation, and thanks everyone for coming. So today I will talk about some previous work I've done with Dongming Gain, Yang Kong Ko, Saming Li, Arthur Liebstein, which is here, as well as Wei Ming Chen, and some recent work that is still in progress with Simon Kieran Hoyt and Theo Bargier, Song Hei, and Tristan McNaughton. So before I begin on the discussion of some three-dimension amplitudes, I'd like to give some motivation or some review of why are we interested in amplitudes beyond 4 dimensions. So there's basically two main motivations. First is we want to address the question that was raised at the very beginning of this workshop, which is how much of these advancement in amplitudes is really tied to 4 dimension, or how much is it really a result of the consequence of 2 plus 2 equals 4. Since if this is really a new approach to perturbative field theory, then since field theory exists beyond 4 dimensions, so it is natural to try to understand how much of these progress can be extended away from 4 dimensions. Now the second motivation would be to address Gregor's zero issue. So the hope is that when we look at amplitudes in higher dimensions, that this will then feed back down to 4 dimension, where in that case the amplitude is not zero, where we have massive QCD amplitudes. And so since these massive theories can be naturally embedded as a massless theory in higher dimensions, so understanding the structure of higher dimension massless amplitude will give us information about how we can construct or more efficiently construct 4-dimensional massive amplitude, where the amplitude is strictly non-zero. So these are the two motivations. And of course, if we want to extend these analysis, the first place we would like to extend to is to a place where there's actually spinor helicity formalism that is closely related to the 4-dimension one. And this exists in dimensions 3 and 6. Now, of course, the hope has been realized has already been realized somewhat. So I would just give some overview of what's been done away from 4 dimension. So some interesting result is, for example, the statement that maximal super Yang mills in arbitrary D is actually dual, in some sense dual conformal. So this has been established in 10 dimensions at tree level, so 10D at tree level by Simon Kieran Hoyt, as well as Donald, who is in the audience, and in 6 dimension at tree level, as well as a loop integrand by Tristan Denon and me. So the interesting fact about this is that, of course, the theory is not conformal at all in D dimensions. So even though the classical, the conformal invariance is not there, but somehow the dual symmetry is actually there. Now, of course, this then feeds down to the fact that the Coulomb branch, the amplitude on the Coulomb branch, is also, in 4 dimension, is also have this nice dual conformal property. And this then, so this is massive now, massive amplitude in 4 dimensions. And this then feeds down to the fact that you can now construct the massive amplitudes using this symmetry. And this can help you construct rational terms in QCD. So this is a very useful example where you look at higher dimension and you use the higher dimension symmetry to constrain the amplitudes, and then you go down to 4 dimension, it constrains the 4 dimension massive amplitudes, and then you get something that is important for real physics. Now, of course, there's also the spinor helicity formalism has also been used to analyze the higher dimension theory itself. For example, the 2-0, all possible 2-0 self-dual tensor coupling at 3 and 4 point was analyzed using spinor helicity formalism, and this was given in a paper that I've written with Moshe Rosali, as well as Bartek Czech. And I think Moshe already gave a talk here about that paper, so I won't go into any details about that. And of course, there's also some analysis using similar helicity formulas for general supergravity and super Yang-Mills amplitudes in higher dimensions, which is done by Rutger Bowles and again Donald. So as you can see, there's been a lot of progress that's been made away from higher dimensions, away from 4 dimensions. So in response to one of the questions in the beginning of the workshop, is this applicable to away from 4 dimensions? The answer is yes, and we have a lot of examples where this is not only applicable but also very useful. But the main topic of my talk today will be in 3 dimensions. So then it might be unclear that why 3 dimension will have any relevance to 4 dimension. Well, the reason that 3 dimensions is interesting, there's a few reasons. First of all, in some sense, because the 3 dimension is another place where you do not have helicity, or you do not have the notion of so-called chirality. It actually shed lights into into theories where what happens with amplitudes that you don't have chirality. And why is that useful? It's because in these discussions where we have 4-dimension amplitude, massive amplitude, well, even massive amplitude doesn't have natural chirality associated. And the most useful way, from my point of view, the most useful way in formulating 4-dimension massive amplitude is actually using the non-chiral version of the formulation. And so actually analyzing 3-dimension amplitude also gives you some hint at how such formulation might work. And especially when the formulation has, the theory you have it in some sense a dual conformal symmetry. What is the most natural way to formulate a representation that is non-chiral but have dual conformal symmetry? So that's one of the reasons we want to study 3 dimensions. And the other reason is also related to the fact that these 3-dimension field theory is in some cases, the limits of M theory. So if you want to consider n equals 4, and in some sense when you're studying n equals 4, you're studying string theory. When you're studying these 3 dimensions theory, you're probing some structures of M theory. And in the process of my talk, you will see that some M theory structure starts to emerge in these analyses. Okay, so let me begin. So as the title of my talk, I'm going to talk about, I'm going to start with orthogonal Grassmanian. And the reason I want to start with that is because there are just several topics I'm going to talk about, and each topic is nicely encoded in the Grassmanian structure. So to begin with, let me just review what a Grassmanian is. So the Grassmanian is proposed by Nima Alkarni-Hammad, Clifford Chun, Freddy Cacciazzo, and Jared Kaplan in 4 dimensions for n equals 4 super Yang-Mills. So this is defined as a projective integral over the Grassmanian, which is a K. It's just a matrix, which is a K by N matrix. So this is the Grassmanian. So I is the particle label where you run from 1 to N, and alpha runs to 1 to K. So in connection to physics, the K will be the helicity. So for example, when K equals to 2 is MHV, and K equals 3 is negative MHV. So let me just go over some details of this integral. So first of all, this is a delta function. The Grassmanian is constructed with this is going to be the momentum space twister, not momentum twister, just a momentum space twister. So this was discussed by Nano yesterday. So this is 4/4, where 4 you have the bosonic 4 component, and then you have the fermionic 4 component. The delta function is a product through 1 to K. And the thing that really controls this integral is this minor structure in the denominator, where this is a product of a series of minors. So this MJK is defined as, so well, it's a minor. So it's basically, if I want to write it out, it's alpha 1 to alpha K, and then K minus 1 alpha K. So essentially, for example, you're taking the determinant of a K by K matrix, starting with the first indices, and you're taking the determinant of this matrix here. So the claim is that what this integral gives is that it gives the leading singularity of your amplitude. So the way that you evaluate this is, well, there's actually a more advanced way that is being discussed now in various NEMA's talk, for example, in DESI a few weeks ago. But in the old-fashioned way, what was computed was you use the delta function to first you use the delta function to localize some of your C variables, and then this minor, which is a polynomial of these C variables, become the integral localized on the zeros of these minor. And so then in n you get some function that is a function of these external data W, and these functions are essentially the leading singularity, which is when you have an amplitude like a multi-loop amplitude, and you localize your loop momentum. You completely localize your loop momentum by the propagators, and that final function is the leading singularity, which I'll discuss in more detail later because I'm going to use that to construct my loop amplitudes in 3 dimensions. So let's say, okay, so we have this n equals 4 Grassmanian formula. So let's say if we want to construct a similar thing for 3 dimensions. So let's just start from scratch. What would be the first thing, the most natural thing I would write down? So to begin with, there's a subtlety that I need to address, which is the fact that these twistor variables in 4 dimensions, because the superconformal group is a complex group, so you have a few, these are essentially 4 under the SU4. And so there's a natural conjugate object, which is Z, which is the 4 bar of SU4. But in 3 dimension, the conformal group is real. So what that means is that your twistor variable is going to be self-conjugate. So it's not natural to write down a CZ in 3 dimension because then the Z variable will have to satisfy ZZ. For example, if I use A and B, this has to be delta AB, where A and B is, so A is the fundamental of SP4. So this is a real group, and so this has a self-conjugate relation. So you don't really want to use Z here because you want to use independent variable. So that means that to begin with, the only thing that you can write down is the following. So let's first write down the delta function. We introduce again a Grassmanian constructed with lambda, which is the momentum spinner. And lambda has, okay. So lambda has 2 degrees, so let me just write a delta 2 here. Now, of course, just blindly copying my 4 dimension, then I have to have k equals 1 to, alpha equals 1 to k. So now I begin with this object. Now, of course, this is going to be Lorentz invariant, but it's not going to be Poincare invariant because instead of here where I have a twistor variable and the Poincare invariance is encoded in the entire conformal group transformation, which is just a SU4 rotation on the A index. Here I only have the SL2R index here, which is only the Lorentz group. So I need to somehow get something that actually will impose the momentum conservation. And if you look at how the momentum conservation works, from a little thought, you'll realize that you have to write something like this in 3 dimensions. So it's essentially C dot Ci transpose, where this dot just means that, so for example, if I have my C matrix and I'm taking the transpose here, and I'm dotting it with, so this is I equals 1 to n, this is I equal 1 to n. So I'm doing this transpose. So this will become a symmetric so this is going to be a symmetric k by k matrix. So it has a total of k times k plus 1, or maybe I should put this here. So this has degree k times k plus 1 divided by 2. So a way to say that this enforces momentum conservation is the fact that, so this is enforcing the Grassmanian to be orthogonal to itself, so that it's in a sense null. This condition forces the lambda to be in the Grassmanian, the null plane, and therefore this combination enforces lambda I, and lambda I when you sum equals 0. Okay, so now we have an object here that is Lorentz invariant, and so this is Poincare invariant. So this will produce something that is naturally Poincare invariant. So again, let's just blindly follow the 4-dimension case, and then we do an integral over this k times n matrix And then we need to put something in the denominator. So again, let's just suppose that we just copied that. So let's just put j equals 1 to n, and this is nk. So let's see. Now, of course, then we need to, because this is supersymmetric, so we anticipate that we're going to have to put something supersymmetric. So let me just put something supersymmetric here. So I'm going to introduce some eta variable, which encodes a supersymmetry. But I don't know how much supersymmetry I have. I don't know what kind of theory I want to look at. So I'm just going to keep this free. So that I have n copies of this. So I'm going to fix this n by requiring that this integral, so as I mentioned in the beginning, that integral is, the Grassmannian integral is defined as a projective integral, which means that this thing has to have a vanishing u1 weight. All the u1 weight, by rescaling all the c's, should cancel. So that's how the Grassmannian integral is well defined. So one of the constraints that I need to impose on this integral is to have the projective weight 0. So let's do the counting. So obviously, so this is an n times k matrix. So the projective weight of my measure is going to be n times k. Now this delta function is going to give, since this is delta of a bosonic delta function, so that it gives the minus projective weight. So it's going to give me this. Now this is going to, the delta function is also a bosonic delta function, so this gives minus 2. So this is a product of 1 to k, so this is minus 2k. This is the fermionic delta function, so this is going to be nk. Now finally, I need to take into account of the u1 weights that's generated by the measure. So this, since this is a minor, so there's going to be j equals from 1 to n, so this is going to be, n is a particle number. There's going to be n of these, and each minor, because this is a k by k determinant, so it's going to be minus nk. So the constraint is that this has to be 0. Now obviously, as you can see, so these two directly cancels out. And what you see that in order for this to have projective weight 0, your supersymmetry is going to have to be depending on k. So which is of course physically unreasonable. You can have the number of supercharges actually changing when each k is increased. So obviously this equation is not right. This is not well defined. So one place where you can modify this is why do we need to put this here in the first place? So one of the reason that we want to put this here is because where j equals 1 to n is because we want whatever we're computing, because we're in a planar limit, so we want whatever we're computing to have some sense of a cyclic ordering. And so this minor has precisely that cyclic ordering, cyclic invariant structure. Now, as it turns out, because of because we're not really on the original Grassmannian, we're on the so-called orthogonal, because the Grassmannian has established this orthogonal condition. So it turns out that actually this minor, because of this orthogonal condition, actually satisfies this relation, which times I plus 1 is actually equal to mi plus k times mi plus k plus 1. With a minus 1 factor, which is k dependent. So this is a consequence of this delta function. But what this means is that you don't need to go into the entire range from 1 to n to have a cyclic symmetry to it, because we have this property. So the minimum set that you can have cyclic invariance is actually you just have to go to half of n. So but then you say, okay, what does it mean by half n, and what if n is odd? So you see that here, there's actually hinting that your theory should only have even number of leg that has non-trivial S matrix. So let's just say this is only to 2n, and look at what happens. So then now you have a half here. So obviously this now does not cancel anymore. And then once you solve this, you'll find that you have only a solution where, first of all, n equals to 2k, which reflects the fact that n is odd. And your supersymmetry has to be 3. So this Grassmannian formula only makes sense when you have three on-shell supercharges, which reflects that this is really an n equals 6 supersymmetric theory. So if we really want to construct a Grassmannian formula in 3 dimension, it forces us to land on an equals 6 theory. And that it forces us to be, in a sense, Chern-Simon matter theory, because you know that only Chern-Simon matter theory has the property that you have even S matrix element. Yes?
Compared to this four-dimensional, you don't have these new variables in here in this formula.
Which variable? Mu?
Mu.
Yes, I don't have the full twister, no.
Why? How then will satisfy the dual conformal symmetry there?
So you can show that through this formula that actually this formula is dual conformal invariant. So the point is that mu and lambda, so in another way, the mu and lambda is not independent. That's the problem. 4 dimension here, you have mu and lambda and the conformal group acts independently. Here, because of the fact that your z and z is self-conjugate, is delta, where 4 dimension you have z and w as delta. So you need the full z to have the conformal group. Here, because z is z self-delta, so without the full z, you still can have conformal.
You're saying that at the moment you write this formula, you verify that it's conformal invariant, dual conformal invariant.
Right, it's dual conformal. This formula is dual conformal. And in fact, this is also another way to see that why you land on n equals 6. So remember that so all of this is really coming from the constraint that I want this to be cyclic invariant. So there is this discussion of what kind of, because when you want dual conformal and conformal, the dual conformal generators are non-local. So then there's the issue of it doesn't make sense to have non-local generators but still invariant or cyclic permutation. And actually that restricts your supergroup to SU224 and OSP 6/4 as well as OSP star 8/6. So this will have some, I will comment on this possibility later, which obviously people can see that it's actually a 6-dimension possibility, which I will comment briefly later. But so essentially this Grassmannian, the Grassmannian formula is basically realizing the Yangian of these two symmetries. The n equals 4 and the ABGM is realizing this symmetry. Yes?
If you're forced to have n equals 6, how is the enhancement to the BLG case?
So, well, I'm just having something that has, so this will naturally have a dual conformal and conformal invariance. BLT will not have that. That's the simple statement. Yes. Okay. Okay, so let's analyze, so let's just, since this...
Actually, I'm slightly puzzled here, because of course the Grassmannian on the left that you've written down there is the regular twisted Grassmannian, and that's the one that reflects the regular conformal invariance, not dual conformal invariance.
Yeah, but you can also prove it by transforming, you know that you can transform this into the dual version.
You can transform it.
Right.
But the one you've written down is one that's reflecting the regular super conformal invariance.
Sure.
And so if this one has a similar status, and the distinction is that the dual conformal invariant one has taken out the momentum conserving delta function. So this one here is, in fact, I would say, reflecting the regular superconformal invariance, not dual conformal.
No, yes, this is reflecting the regular, right, exactly. But you can also prove it, which is more involved, that this will give you something that is dual conformal as well. But it's manifesting the conformal, yes. Yeah, that's correct, right. That's manifesting the conformal, right. Okay, so just as always, this is an abstract formula. So let me just use a simple example, example to show what that formula gives. Oh, by the way, this formula was first written down by Sang-Ming Lee, and so this was first, I think it was 2010. And it was later further analyzed in the first paper that I mentioned there, which confirmed that this formula is correct and it has all the properties that one would like. So let's, okay, so of course there's a natural, and I forgot to mention, which is very important, that there's a natural GLK, since this C variable is really a K by N matrix. So this formula is obviously invariant under a GLK rotation under K indices. So in order for this integral to be well defined, you need to mod out this GLK orbit. So you need to do some kind of gauge fixing on the GLK. So let's look at the first non-trivial example, which is K, so which is a G2, 4, so K equals 2. So I'm going to do my GL, so I have a GL2 symmetry that I can, so G24 is essentially you have K equals 2, so you have C11, 2, 1. So this is your matrix that you're looking at. Now I'm going to do a gauge fixing, so I'm going to use a GLK to gauge fix this to be 1, 0, 0, 1. So now I've used away my GLK. So let's see what this delta function means. So this delta function is enforcing, so delta C lambda now becomes enforcing the condition where you have lambda 1 alpha. So I'm going to relate C1, 2. I'm going to relabel this as 3. This is just relabeling, so it doesn't. So this is enforcing this condition and also enforcing so from this, one can see that you can immediately solve for C1, 2 equals to minus 4, 1. So you just multiply by the spinners, by spinners that project out one of them to set one of them to 0, and the other one will come out. As one can see, so essentially the delta function completely solves your C variables after your GL1 fixing. So, okay, I should mention something. So I'm going to, since I already have, I'm taking this example, let me just prove this relation. So it's always to prove a relation by example. So if you look at so I'm going to prove M1 times M2 is equal to M1 plus M3 times M4 equals 0. And I'm going to claim that this is 0 because of this orthogonal condition. Now, by looking at this, one can see that M1 is essentially just C12, C32. And so let me just write it repeating here. So this is C32, this is times C12, because this is just a minor. So M1 is taking this minor, so this is C32. M2 is this minor, which is C12. M3 is this minor over here, so this is minus C14. And finally you have a minus C34, so it becomes plus. So in order for this condition to be true, this has to be true. And you can take, so then let's look at C times C transpose, which is actually this times the transpose of itself. And it's going to be a 2 by 2 matrix. And you can see that this corner, which is basically this times this leg, is essentially just C12, C32 plus C14, C34. So it's exactly this condition. So you see that the fact that this satisfies this identity is a reflection of the fact that your Grassmanian is orthogonal. And so, but of course you can go through a more rigorous proof to see that this is true. So for those who've listened to Nima's talk and Desi, that he discussed that actually the Grassmanian of n equals 4 contains the ABJM Grassmanian. What he really means is that in some sense the ABJM Grassmanian is really just an additional condition that you impose on the Grassmanian coordinates that it has to be orthogonal. So in some sense it's a subset of the n equals 4 Grassmanian when you're doing manipulation with it. Okay. So once I have this, we can see actually what this Grassmanian gives. So I'm just going to write out what each component becomes. So, for example, delta C lambda. Even though this C lambda is enforcing this condition, but there's really a Jacobian factor. So the Jacobian factor gives you back 4/2 square after you solve that. And then delta C times eta, this becomes delta 2q times 1 over 4/2 delta CC trans. So this is actually a degree 3 because k equals 2, so it's a symmetric 2 by 2 matrix. And this becomes delta, not surprisingly, momentum conservation times 4/2 to the cube. And the minors you can just directly compute. At the end of the day, what you obtain for k equals 2, n equals 4 is simply delta P3 delta Q6 divided by 1, 2, 2, 3. So this is what this computes at k equals 2, n equals 4. So this is precisely the 4-point amplitude. Now the next case, so I'm just going to write out the next case, which is k equals 3, n equals 6, just directly, because it's going to be useful in my discussion of higher points. So let me just write, so when k equals 3 and n equals 6, so this will correspond to 6-point leading singularity. The answer is, the leading singularity is given as, again you have the delta function it will be interesting to look at what the form of this is. So cyclic means cyclic in these three indices. So you see the even and odd lines are separated. And notice that there's this I sitting around all over the place, and that's simply the fact that you're solving a quadratic equation when you're solving the CC transpose. So this times the 2 cyclic orbit, cyclic by two sides, and then there's 1 over P135 squared. And there's also another one which is just the complex conjugate. Now there's really since this is just a complex conjugate, so there's really only just one object that is coming out from that integral. So actually you can count the number of integrals that you need to do. So essentially since you have 2k times k, so n has to be 2k. So you have 2k by k variable here, and you're localized by this delta function, which minus k times k plus 1 divided by 2. And you're localized by this condition, but then some of this is a momentum delta function. So you minus 2k condition from the bosonic variables plus, but then you have to subtract out the fact that some of that is really just momentum conservation. In the end, what you have is you have an integral over a dimension of 2k minus 3 times k minus 3 times k minus 2. So you see that when k equals 2 and k equals 3, there's no integration to be done. And that's why you only have the one object that is coming out from your Grassmanian. So you have the 4-point and you have the 2 leading singularities. Well, it's actually just one because the other is just a complex conjugate at 2 and 3. But beyond when you start at k equals 4, which is an 8-point amplitude, now you're starting to get more and more objects because you have integral that needs to be localized by the minor here. Okay, so we have this Grassmanian and it's computing the leading singularity. So what do we mean by computing the leading singularity? So I will take this 6 point as a first non-trivial example, and the 4 point will be the 4 point will be just a degenerate example. So what this is computing is, let's consider a one-loop amplitude in 3 dimensions. And you can so since you have 3 degrees of freedom in your loop momentum, you can cut 3 propagators. And so once you cut 3 propagators, there's 3 conditions that localize your loop momentum. And so once you cut 3 propagators, this has to factorize into 3 tree amplitudes multiplied by each other and evaluated on the solution of the solution that is satisfied the fact that all 3 propagators are unshelled. So this is localized on a particular solution. Now, of course, you have to multiply it by a Jacobian factor, where the Jacobian just comes from the fact that you're solving 3 quadratic equations. And the Jacobian factor, so if I use dual porters, let me just call this I, J, K. The Jacobian factor is going to be 1 over xij. So it's just the length of this. So it's just the length between these dual coordinates. So this will be my Jacobian factor. So what the Grassmanian is computing is really computing this object where you have 3 tree factors multiplied divided by this Jacobian factor. Now one can explicitly show that at 6 point, what I've just computed over there is exactly what you would obtain if you compute the 6 point result. So, but then the first objection that you can raise is, wait a minute, I only have one object up there, but if I look at the 6 point, here, let me just use this. So this is a 6 point. So there's really 2 kinds of cuts. There's really 1, 2, 3, 4, 5, 6, and obviously there's the other cut, which is just rotation by 1. So there's really 2 sets of cuts at 6 point. So this is a bit curious why you only have one object up there. And the reason is that actually, so since this is the dual coordinates will be x5, x1, x3. So the statement is that this cut divides, so let's say, so the statement is that this cut with this particular 4 point amplitude multiplied each other divided by this Jacobian factor is actually the same as the other cut if you do the rotated by 1. So this thing is actually cyclic invariant. So that's why you only get one object. Now, what happens at 4 point is becomes a little bit singular because, as you can see, if I go down to 4 point, let me erase these 2 legs. I have 1 and 2. Then one has the problem that, okay, so this is a 3 point. These 2 are really 3 point kinematics. So we have the problem that that the amplitude is going to vanish, and especially since we're in 3 dimensions, there's no sense of going to complex kinematics is not going to help you. But of course, this limit is also well defined, since if you can. So before doing this, you can easily see it by this way. Before, let's say we don't cut this leg, we just cut these 2 legs. Then the solution of cutting these 2 legs, you can actually parameterize that. So let me call this PL1, and let me call this leg PL2. Then PL1 you can parameterize by, since this has to be unshelled, so the unshelled lambda is going to be, you can parameterize as a lambda 1 times sine theta plus lambda 2 times cosine theta, and PL2, the lambda for PL2 is going to be I lambda 1 times cosine theta minus lambda 2 times sine theta. So there's there's one parameter family of solution left because you're putting two conditions, and this parameter is parameterized by theta. You can show that this solution will satisfy momentum conservation in this configuration. So what happens when you cut this leg is what happens here is that then this isolates theta into not to be pi over 2. So when you cut this becomes soft, and what happens is that this leg just becomes equal to P1, and this leg becomes equal to P2. So you basically, it becomes a 4-point configuration if you put theta equals pi over 4. So that's essentially in that configuration. We have so for these massless legs, when you cut these three, what happens is this becomes soft, and you just have parallel. You just have this directly going into P1 and this momentum going into P2. So this will be very important because this will allow me to fix my integrand very fast. Okay, so this is just this particular singular limit. So in that sense, when you're computing the leading singularity for the 4-point, what you should get is just a 4-point tree in the end, because the momentum is just flowing directly into the 4-point tree, and that's exactly what we found when we computed the 4-point Grassmanian. Okay, so since I know what my leading singularity is, I'm going to use that as information to fix the integrand of my loop expansion, of my loop amplitudes. So I will discuss two cases so in the first one, I'm going to discuss my 4-point multi-loop correction. So let's just start at one loop. So the idea is, so the procedure is the following. You want to construct, once you know the leading singularity, what you want to do is you want to first construct an integrand such that the integrand has unit leading singularity, which means that if you put the integrand on 3 cuts, then it's going to give 1. And then you multiply that integrand by the leading singularity that you computed from the Grassmanian, and the claim is this is going to be your amplitude. So what is the unit leading singularity integrand at one loop? It's given by this. So let me just write it down. So I'm going to parameterize my coordinate x1, x2, x3, x4, and let me just call this xa. So I'm going to use dual coordinates. And second of all, I'm going to use embedding formalism. So embedding formalism just means that I'm embedding my 3-dimension space in 5 dimensions. So and on the 5-dimension projective light cone. So I'm going to use big X. So I'm going to embed my 3-dimension coordinates and d equals 3 into 5 dimensions, where the 5-dimension coordinates satisfy x squared equals 0. This is on a null plane. And the reason is obvious because the conformal group is really the 5-dimension Lorentz group. Okay, so once I use the embedding formula, it's very easy to write down what the integrand, the leading singularity integrand is. So it's going to be given by, so I'm just going to write IA1, 2, 3, 4. So this, let me just use a 5 to indicate that this is a 5-dimension Levi-Civita. A dot x1, xa dot x2, xa dot x3, xa dot x4. So this will be the unique integrand that is first dual conformal, and actually you can check that this actually has unit leading singularity. And then a straightforward way to check. So probably a few comments. Right, so this Levi-Civita means that when I'm writing this, it means that I'm having a 5-dimension and contracting with A, mu, 1, V, and etc. x5, x4, tau. So this is what this Levi-Civita means in 5 dimensions. So first of all, let me just show that this has unit leading singularity. So let me just, let's say I cut these 3. So first of all, this you can expand this out, and once you rewrite this in 3 dimensions. So if you rewrite this in 3 dimensions, what you will have is, so let me just write this in 3 dimensions. What you have will be x1 squared. Now this becomes now this becomes a 3-dimension x. I think this is smaller than this, so I guess this you can tell that this is 3 dimension. So A1, 2, 3, 4. So this is a 3-dimension Levi-Civita, and you have minus xa 2 squared epsilon 3, 3, 4, 1. 1, 2, 3. Okay, so this is what this numerator looks like. So if I cut these three propagators, I'm cutting, so I'm essentially removing xa1, xa2, and xa4. So I'm putting these three on shell. Then that means that xa1 here is on shell, xa2 here is on shell, xa4. So these numerators are 0 on this cut. Oh, this is 3. Right, okay, good. So this numerator is 0 on this cut. So the only numerator left you have is this. And you see that on this cut, xa3 is on top of xa3, so these two cancel with each other. And you're left with epsilon 3, 1, 4, 1, 2. So what is epsilon 3, 4, 1, 2? Epsilon 3, 4, 1, 2 is exactly the length of 4, 1. So 4, 1, 2 is exactly, as everybody knows, just the length of, it's a triangle. So it's a triangle of 3, it's a length, multiply the product of the length of a triangle. So x4, 2 and x1, 2. So obviously, remember that when we're doing the cuts, there's a Jacobian factor, and the Jacobian factor will eat up this factor remaining in the numerator. So once the Jacobian factor eats this, indeed on the cut, everything cancels out, and this is 1. So this is just showing that this integral is really unit-leading singularity, has unit-leading singularity. Okay, so besides having unit-leading singularity, the other property of this integral is that it integrates to 0. So if you actually integrate it, this thing gives you 0, and there's an easy way, so you can see this by just doing Feynman parametrization in 5 dimensions and integrate it. Anyway, so that's a little bit you can see, so it's probably too detailed to show that. But the statement is that this is 0, and this is 0 is very nice because it matches with the Wilson loop computation. So the one loop 4 cuts Wilson loop was computed by Johannes Hen and Yang Plafka and I think Constantine showed that the 4 cups Wilson loop is 0. So we have a nice match of 0 with 0 at one loop.
Well, it's the 4 cups Wilson loop in 3 dimensions.
Right, 4 loop ABGM Wilson loop. So, but as you can see, by forcing that this is very interesting because we were expecting a 0. But then we know that we should have a non-trivial integrand because when you do the cuts, you see that you have factorized into 4.3. So it was a bit bizarre at the time, but actually you can see that using leading singularity, we know that there's a unique integrand, and the unique integrand directly lands us with the right one that satisfies the cut condition and actually integrates to 0. So let's go now move to, I'm going to save this because it's going to be useful later. So let's now move to 2 loop, and you can use the same procedure to fix a 2 loop integrand. So it's just essentially 2 minutes of work. So 2 loop integrand. So the way you can do this is the follows. So first of all, I know that, let's say I start with a double box, and I know that if I do these 3 cuts, it's going to localize this to a 1 loop integrand, and I know what the 1 loop integrand is, which I derived before. So this actually tells you that your 2 loop integrand, so let me call this 1, 2, 3, 4, and A, B. The 2 loop integrand has to take the form. So I'm not going to write out the propagators. The propagator is just a double box propagator. So I'm going to just write out the numerator. The numerator is A, 1, 2, 3. And then B, 3, 4, 1. So these are the 5-dimensional Levi-Civita tensors. And what this star means is just that these 2 indices are contracted. So you have 2 Levi-Civita tensor with 1 free indice here and 1 free indice, and these 2 indices are contracted. And it's easy to see that if you do the maximal cut here on this subloop, what happens is, recall that when I'm doing the 3-point cut, I'm essentially what I discussed before. You essentially this becomes soft, and this just these 2 particles coming in. So what this becomes soft means that A goes to 2, and you can see that this contraction leaves you with the numerator of the 1 loop subintegrand. So this actually this just fixes your 2 loop integrand. But there's a caveat, is that we know that if you do this cut, you're cutting a 3-point here, and this should vanish. So, but this has a bad cut appearing here. So you need to modify it. You need to do something about it. And what you do is you simply add this integral which do not have the maximal cut, but it has exactly this cut feature, and the numerator of this is essentially fixed. Well, it's fixed by, the numerator is fixed by dual, so let me just 1, 3 here. The numerator is fixed by dual conformal symmetry, but the relative ratio is directly fixed by just analyzing that on this cut, that these two have to cancel out. So just doing these two steps, you fix your two-loop integral, and you can check that this matches all the cuts in the discussion. So of course, this is the S channel, but then you need to add the T channel. The T channel version of this. So what's interesting about this computation, about this integral, is that it directly matches again with the Wilson loop at two loop. But there's this, in some sense a refined matching in the sense that, so let me just, so this is this plus S goes to T. This integrand is equal to the four-cups Wilson loop, where you have Chern-Simon matter correction. And this plus S and T directly equals to the pure Chern-Simon part of your four-cups Wilson loop. So in this case, you see that the amplitude Wilson loop duality is somewhat more refined. So in these particular processes is dual exactly to one particular integrand, and the other, so there's actually a reason why this splits into these two, because you can classify your Wilson loop into two different kinds of process. Yes?
You imply hypothetical gauge.
Excuse me?
The statement you make is gauge dependent statement. So you choose particular. When you define diagrams on the right hand side, you imply.
You mean for the Wilson loop?
Yeah.
Right. So
Understandable why? You just, I understand the statement, but it's presuming Feynman gauge, right? You're saying.
yeah, I think they computed in Feynman. Right.
Also, the matching is between the logarithm of the amplitude in this case? Or
Yeah. The what?
The matching usually is with we calculate the logarithm, so we subtract one loop squared. So here it seems that it's.
Well, there's no one loop, right?
There's no one.
Oh, there's no one loop, right?
So this is like the first place,
That's
or right? So it's a.
Sorry, what? Those diagrams are one loop too low, right?
Which diagram? So this is a two loop,
Right.
and this is two loop.
Oh, and this one is a one loop?
Which one is the one loop?
Well, you have a single gluon exchange.
Oh, sorry. Yes.
Alright,
Okay.
I
Yes.
see.
Sorry. Yes, this is my fault. Yes, of course. Okay, and actually, in the Wilson loop computation, it was shown that actually the two loop Wilson loop, the sum of these two, exactly has the same formula as a one loop n equals 4 Wilson loop. So since I have the amplitude matching with the Wilson loop, that means my amplitude is the same as n equals 4 one loop amplitude. So here you have a very interesting structure where you have the duality between four different objects. So you have so I'm just this too. So you have n equals 4 super Yang Mills, which has the Wilson at 4 point. So this is one loop. I'm just talking about 4 points. So you have the 4-point one loop amplitude is dual to the Wilson loop, 4 cups Wilson loop. But then the Wilson loop is dual to the ABJM 2 loop Wilson loop. And then now we've shown that the ABJM 2 loop Wilson loop is dual to the ABJM 2 loop amplitude. So now you have this nice square. Now once you see that there's just a close relation with the ABJM n equals 4, the natural thing is to ask is, so does this mean that BDS is actually the answer for two theories, at least at 4 point? And of course, there's actually this relation between, close relation between ABJM n equals 4 was also observed when one was computing the anomalous dimension, where one finds that you just basically substitute the n equals 4 answer by a function by a coupling constant dependent function, but then you get exactly the ABJM custom anomalous dimension. So of course, then the question then becomes since the infrared divergence of the theory is controlled by the custom anomalous dimension, it was also by the collinear as I mentioned. And so the question, so since the cusp is matching between the two, and the one loop and the two loop is matching to the two, the question then becomes whether or not if the collinear divergence, the collinear analysis dimension is also matched, then this will imply that the two theory is exactly the same to all loop order, at least at 4 points. Now, of course, the exact match of the two theory cannot be true, because we know that ABGM has only even points. So what does this mean for higher points? Now, one conjecture is, so what would be so if there is really a relation between ABGM and n equals 4, then n equals 4 must have some property that only appears at even point. And one property is the fact that the next to MHV or next to KMHV, the true one that is not, so for example, a 5 point has next to MHV, but it's really an MHV bar, so it's not really a true next to MHV. So the true next to KMHV always appears at the first place it appears is at even points. So the natural conjecture would be that ABGM is reproducing n equals 4 next to KMHV at each order, or at least it contains the same function.
There is another problem that you think about kinematics. Kinematics is a
Yeah, of course it's reduced. So you can think that, okay, so n equals 4, and then you just reduce the 3-dimension kinematics, and that's supposed to be ABGM.
Yeah, no, but thinking about Wilson loop in n equals 4 theory, which is planar one, lying on the plane. The one which composed of the segments which lie on the plus-minus plane.
Right.
So this kinematics is exactly the one which appears also in 3 dimensions. So if I'm thinking about comparing Wilson loops, but not Wilson loop computed n equals 4 3 and n equals 3. There is a common configuration which live in both kinematics, which are planar configuration.
So what the problem is?
No, I'm saying that the
Right. Okay. Oh.
the natural place to look just exactly for the
But
planar.
okay, so here's the problem. That cannot. It's not going to be that because the very simple, the bosonic Wilson loop is not going to be dual to the amplitude beyond 4 points. Because for example, as you can see, the 6 point has fermionic degrees of freedom. So, or another way to frame this, there's no such thing as MHV. And so in some sense, the bosonic Wilson loop is computing the MHV of the n equals 4. But there's no such thing as MHV and ABGM. And in fact, the relationship between it looks like once you go to 6 point, you're dualizing to the next to MHV, if you do the fermionic counting. And that would say that you really, it's not right. So this is not that trivial, not entirely.
Are there any proposal for strong coupling for BGM theory? For the kinetic amplitude?
Strong
Coupling expression for example.
You mean in terms of Wilson loop?
Minimal area.
Yes, of course. There's obviously the 4 point. You can compute the 4 point, and actually it matches with what you would expect. But the question is really higher point than how does. And of course, this goes back to the original the point that Arthur mentioned, which is the question: how does, because ADS4 cross CB3, if you try to do T dualization, go through this business, it just doesn't work. You'll encounter singularities at it. So it's very non-clear. At the string picture, in the string picture, where is the origin of this dual conformal symmetry is just completely unclear. Even though it's been proven in perturbative field theory. So let me just present you with the 6.1 loop result. So you can use this, since we already have the 6 point leading singularity, you can very easily compute the 6 point result. Let me just give you the 6.1 loop. And it's very interesting because this is where you see that you actually, ABGM contains more than just an n equals 4 function. So since I'm running out of time, I'm just going to write the 6 point integrand now. So this is work with Simone. So this consists of these two. So there's box function, which again have this epsilon tensor, Levi-Civita tensor. I'm just going to write the form of the integral. So you have these two forms. You have one massive and two mass hard integrals. But even though this is 2 mass hard, it's 0. So it's not hard. So this times a tree. Then you have the two triangles, 1, 3, 5, 2, 4, 6. And this is multiplied by 1, 2, 3, 4, 5, 6. and this is multiplied by 1, 2, 3, 4, 5, 6, 1. And this is multiplied by the one loop leading singularity that I computed here. So this is the one loop result. And what's interesting about this, like I said before, the fact that the 4.1 loop with this kind of integral integrates to 0, actually you can easily show that this also integrates to 0. So this is just 0. So you really only have this piece here. And after integration, you'll find that this piece is equal to, so after integration, this piece is equal to and divided by the length. Okay, so if you actually went to compute what x13 is, so x13 is p1 plus p2 squared, and then you take the square root. But this is absolute value, so you see that these are exactly the same thing up to a sign. So in fact, the denominator is exactly the same thing as the numerator up to a sign. So then the same thing that goes here. So that means that this is essentially just plus minus 1. And this is also just plus minus 1. So this means that this can be either leading singularity times 2 or 0. So that means that this one loop correction is actually a step function. So the step function so the one loop is equal to the leading singularity 2 times leading singularity times the step function of the sign of this kinematic invariant. So there's various ways of writing this, but one way is to write trace of P1, P2, P3, P4, P5, P6. I don't know. I mean, this is just what it comes out to. So this is, I guess, analytic S matrix is just out of the window. But this is so interestingly. So as you see, the ABGM actually contains new functions. And at two loop, you can use the similar method to fix a two loop integral, which we're now integrating. But like I said, the conjecture is that two loop you're supposed to see next to MHV structure of n equals 4, and there is a hint that it is true because, for example, one of the integrands that appear at two loop is with the following combination. So you have the two loop. At two loop, you have this integrand with again the epsilon plus this integrand. So if you believe that at two loop 4 point, the combination of this is equivalent to 4-dimension the four box integrand, then then it's probably not too far-fetched to believe that this is actually equal to this, the 2 mass hard integrand in the 4 dimension, which only appears in next to MHV. But of course we need to finish the entire integration, which we're working on that now. But it appears that the 6.2 loop answer actually contains a piece that is next to MHV n equals 4 plus some additional piece that is actually the daughter of these weird functions. Okay, so this is interesting. This is a story of loop amplitudes in ABGM. So I'm going to close with some interesting behavior of tree-level amplitudes in ABGM. Yes?
Is there any general statements about functions which can appear, like no triangle equality? Is there any Any similar statement here?
No triangle.
Any statement on which integral functions can appear?
Not that I know aware of. I think people just have not really.
It's four in 3 dimensions, so you should expect only triangles, one would think.
A lot of bubbles.
Yeah.
Yeah, of course. We already have triangles.
Boxes when you integrate go to 0.
Okay, so let me just go very. So of course, one of the things about doing tree-level amplitudes and doing BCFW is that you want to have large Z fall off. You want to have sufficient large Z fall off. Since I'm claiming that my Grassmanian is computing the leading singularity and the sum of leading singularity gives you the tree amplitude, it's sufficient that I just analyze the large Z fall off of my Grassmanian. So this is the simplest way. Of course, then you have to justify whether the Grassmanian actually gives the amplitude of the theory. But if you believe that, then you can analyze the large Z fall off of the Grassmanian. So we can do that directly. And what you will find is the following. So I think Arthur mentioned what the BCFW shift in 3 dimension is yesterday. So it's essentially you have, let's suppose that I'm shifting lambda 1 and lambda L. So then the shift that you would have is just V minus 1, I, V minus V. And the minus of this, and Z plus V1 half, minus lambda 1, lambda L. So let me just call this matrix RZ. So when I'm doing the shift, I'm essentially multiplying my lambdas with RZ, and similarly, I'm multiplying my eta with RZ. So that means the shifted Grassmanian, so let me just call this, okay, the leading singularity will come out of this. So the shifted Grassmanian, I'm just put a hat here, is just going to be something with here that I insert RZ in here, and let me insert RZ in here. Now I can do a change of variables, so let me define C tilde equals to C times RZ to absorb the RZ into the Grassmanian. So this means that I change this into tilde. Now since RZ transpose RZ is 1, I can directly just change this to tilde without introducing any factor of Z. And since this matrix has unit determinant, that means there's no Jacobian if I just change this to tilde. So now you see that all the Z factor is going to come from your minor. So it's easy to see that your minor is now, so let me write the C matrix here. The C matrix is going to be, the C tilde matrix is now going to be some C1 tilde, now with some Z dependence, C2 dot dot dot, CL tilde, with some Z dependence, dot dot dot, CK. So one can use this to deduce that, for example, M1, so let's focus on when L is smaller than K. So if L is smaller than K, then since L is smaller than K, when you're taking a determinant, both of these Z's are appearing and they cancel each other. So M1 is independent of Z. So so this M1 is going to be independent of Z. So M, then you can deduce MI when I is bigger than L is also independent of Z. And only when M2, when I is between 2 and L, you have linear in Z. So that means that your leading singularity has the following fall-off behavior. It has Z. So if you shift legs lambda 1 and lambda L, so it's going to have Z L minus 1. Your shift is going to have 1 over Z L minus 1 shift. So the further you go, the faster it's going to fall off. This is going to be reflected in the amplitude. And what this means in the amplitude is actually, as some of you know, when you have improved large Z falls, what you're going to have new relationships between the amplitudes. And for ABJM, what you can show that a new relation is exactly the same linear relation that was shown by Tilbarger, Songhe, and Tristan McNolan, the BCJ relations. And the way you show this is a simple example is that if you take the 6-point, so the 6-point amplitude so let me just give you a brief example of how this is done. So you start with the 6-point. So the 6-point satisfy the U1 like identity. So let me just write this identity out. So 2, 4, 6, 4, 6, 2, 6, 2, 4, 2, 4, 6, 4, 6, 2, 6, 2, 4. Okay, these add up to 0. Now I shift 1 and 2. This still has to be 0. But now I put it into integral, a dz integral, and I multiply the whole thing by S1, 2, 3 z factor. This still has to be 0. But since once I multiply S1, 2, z, since these non-adjacent shifts had better than 1 over z squared fall off, this thing will integrate to 0. So the result of this integral is you have some linear functions of S1, 2, 3 times a tree, for example, plus some other linear combination which has to add up to 0. And this linear combination you can directly look up in Tristan McNolan's paper and these collaborators their paper, and you can see that this is exactly the BCJ relations they find. So, of course, this is only using 1 over z squared. So the question is, you can iterate this to higher points, and you can show that this continues getting the BCJ relation, which matches the 3-algebra structure of your theory with the 3-algebra with the kinematics and square root of gravity, which is discussed by Henrik yesterday. So the question is, what is the new higher for when you go for higher points? You can have even better when you're going further and further apart. You can have better behavior. So the question is, what is that behavior telling us? And actually, if you go back to the original n equals 4 Grassmannian, you can do this analysis again. And what you will find is that it is known that if you have non-adjacent shift, you have 1 over z squared fall off. But actually, if you have next to KMHV, you can have at most 1 over zk fall off. So for example, if you look at you take Nima's paper, the duality of S matrix paper, you look at the 7-point leading singularity that he computed, and you shift 1 and 5, and you'll find that it has a 1 over z cube fall off for next to MHV, 7-point next to MHV. And if you go to higher points, you have 1 over z fourth and 1 over z. So there's better fall off. And of course, when you ask what is the relationship that is implied by these, the natural first reply is that, okay, it's just a higher level BCJ. But obviously this is not true because this is actually k-dependent. So whatever bonus relation that will come out of this improved behavior fall off is actually going to be a k-dependent relationship. So I think it'll be very interesting to actually look into what these relationships imply. So let me just conclude with some concluding comments. So in this talk, I've shown that so first of all, in this talk, I've shown that actually ABJM. Originally, we were thinking that ABJM is a subset n equals 4, but it turns out that it's not a subset. It's actually at 4 point it's equal to n equals 4, then it's not equal to, and then we realize that at 6 point it appears that ABJM is actually perhaps n equals 4 is a subset of ABJM, the functions that appear. So this is a very interesting relation between ABJM and n equals 4, and I think is interesting to actually investigate further because these relations are both controlled by, actually, since well, what I want to say is in some sense, one can argue that these relationships are controlled by integrability. But actually, if you look at the Grassmannian format, you would say that ABGM is a subset of N equals 4 because the Grassmannian is subjected to additional conditions, so it has to be a subset. But somehow, when you look at the amplitude, it turns out not to be the case. So actually, this might imply that even though the Grassmannian gives you the leading singularity, and ABGM leading singularity is indeed a subset N equals 4 leading singularity. But because of the three-dimension kinematics, it has actually produced some new interesting function that is not the same as N equals 4. Now, so there's a lot of interesting questions that can be posed. I think the most present is actually what is the dual object? So as I mentioned, there's an amplitude Wilson duality at 4 point. But this is obviously not true at higher point. But then one would expect that you need to introduce fermionic Wilson loop. But then the way that N equals 4 works is not really the same as ABGM, because again there's this issue that for N equals 4 next to MHV you have multi-points that can describe it next to MHV. But for ABGM it's only the 6th point that will possibly match the next to MHV. At higher point you just have to increase more and more. And this is also due to the fact that N equals 4, when you're doing the Wilson loop, you're really factoring out a MHV piece. And what the Wilson loop is computing is whatever that's remaining that you factorize out. Here, there's nothing to factorize out. So, and actually, the situation is, which was why sometimes I come back to this very often, is actually the ABGM is more closely to this non-chiral version of N equals 4. Where in the non-chiral version, you also have this behavior where you have each point, you have each increasing fermionic degree, and it's always uniform fermionic degree at each point. And since this non-chiral version of N equals 4 also has dual conformal symmetry, so actually the two questions are related. What the dual object is for non-chiral N equals 4 is going to be related to what the dual object is for ABGM. And actually this also very interesting, also connects to another question, which is the non-chiral version of N equals 4 is directly related to the higher dimension N equals 4 theories. Because if we look at the higher dimensions, as I mentioned in the beginning of my talk, higher dimension in maximal super YAMLs has dual conformal symmetry. So how do we realize this? Once you realize this in dual space and dual X space and dual theta space, you'll find that when you land in 4 dimensions, it's actually a non-chiral version of N equals 4. So all these questions are related to each other. The dual objects for the 3-dimension theory has a relation to the N equals 4, non-chiral and X has a relation to the higher dimension N equals 4, which goes back to the original purpose of understanding the higher dimension N equals 4 is that it controls what the massive amplitude looks like. So if you can, so as is well known, that we can use dual conformal symmetry to give you very efficient method to give you QCD amplitudes because it is organized in a dual conformal invariant form embedded in N equals 4. If you have the massive, if you can utilize this massive dual conformal symmetry, you can give massive QCD amplitudes very efficiently. So that's one of the purpose. And obviously, the next question is as these authors showed that there's a duality between, they use ABGM amplitude to construct the BLG amplitude and show that there's a duality between the 3-algebra of BLG with a N equals 16 supergravity. We know that ABGM also has its own 3-algebra construction. And actually you can show that there's also a color kinematic duality for the 3-algebra structure for ABGM itself. So the question then becomes, is all the 3-algebra that actually exists for the Chern-Simon matter theory all have their own color kinematics duality? Then if that is true, then they would imply that each of them have their gravity dual in terms of by squaring them. So it is known that there's N equals 5 3-algebra structure as well, and there's also I think N equals 4 as well. So it looks like, so it really looks like 3-algebra is not for gauge theory; it's actually for gravity. Yes, and I think I'll end my talk on that, even though I didn't write it out, but it's recorded. Yes.
Any questions?
Yeah, so I have 2 questions. So your one loop computation at 6 point, does that tell you anything about a possible dual Wilson loop?
Well, the problem of dual Wilson loop is already a tree-level question.
Okay, but I mean, does that provide any additional hints?
It provides additional constraints.
Constraints or hints or?
Well, constraints that it has to be reproduced.
Right. So are there any? Okay. So, but
Yeah,
Beyond that,
I mean,
is there
already
anything-
at tree level. I mean, at tree level, this is the amplitude. Okay, if you want to, I mean, we can look at the tree level, and it's very bizarre because the tree level have these i's in the denominator, so this will look very spurious. But actually, there is no spurious pole here. Actually, if you actually look at it, so so the question is, how do you use a Wilson loop to describe this object?
Okay, and one more question. So at tree level, at 6 point, it's not possible to write down anything with 6 supercharges. The 6 point amplitude has to have 9. It has to have fermionic degree 9.
Sure.
But this might be a silly question, but what about at loop level? Is it possible to construct a loop level amplitude that has 6? Fermionic degree 6, or
Well, at least the loop level that we construct still has 9. It's uniform. I mean, the 9 is uniform, is independent of loops.
So
right?
I guess
It's just
another-
R symmetry that we restrict it to 9.
what I'm saying is it possible for an amplitude to vanish at tree level but be non-zero at loop level? An amplitude with a certain fermionic degree.
Well, there's definitely the plus, like QCD has the all plus amplitude that's vanishing at tree level, but it appears at loop level.
Okay, so maybe one can.
Right. So then this will be the statement that I guess then there will be something that is not cut constructible.
Okay, because just by analogy with
Because when we're constructing, we use cuts and we obtain. But I don't. But with this large amount of supersymmetry, I don't have a definite answer for that. But I think with this large amount of supersymmetry, it's unlikely that there's a not cut constructible piece that we missed here.
Okay.
But this is a valid question that we should yeah.
And the underlying motivation for this question is if you want to construct a Wilson loop by analogy with n equals 4 super Yang-Mills, and you sort of view these the endpoint amplitude. I mean, for example, you view the 6 point amplitude as being roughly like the split helicity or the NMHV 6 point amplitude in super Yang-Mills. Well, that appears at the same order as the one loop correction to the MHV amplitude at 6 point, and so that would suggest, that maybe even though an analog of the MHV amplitude doesn't exist at tree level, perhaps there is it exists at loop level, some analog.
Sure, you have to find it first.
Right.
Yeah. Yes, Tom.
How large is the minimal basis for amplitudes, tree-level amplitudes in AVGN?
You're thinking about zero like n-3 factorial. We haven't done this analysis thoroughly yet, so I don't have an exact answer right now.
You know, in a couple of examples, we can extrapolate.
Well, I mean, I only know 4 and 6 point up to now. So, for example, the only non-trivial, so the non-trivial identity at 6 point is only the U1 decoupling identity that you have. So I think the reduction is not going to be a -3 factor. It's going to be significantly less because you don't have that, right? But then you have this new BCJ relationship. So no, I haven't done the counting. Sorry.
Any other question, James?
You were going to mention OSP86.
Oh, okay, sorry. That's a 4 I did not mention here, but that was something like this. So obviously, so what we were looking at was orthogonal. So this is a very natural question. If you have orthogonal Grassmanian, why can't you have symplectic Grassmanian? So what does symplectic Grassmanian mean? So it means that, so let's look, so what remember what orthogonal Grassmanian just means that you have this condition. So you're imposing a constraint on the symmetric product. So a symplectic Grassmanian will require you to put a constraint on a symplectic product. Now, to introduce a symplectic structure, what you would want is and for example, in natural things, to introduce an SU2 index. So this, now you have a symplectic structure. But what does this SU2 index do? So if you try to multiply, we know that C has to multiply with lambda. So that means this SU2 index has to multiply by lambda, which carries an SU2, which is a 6-dimension lambda. And if you, so you can, then we can just go through the exact analogy there. And actually, you will find that if you again, so if you again, so the statement is the following: if you again impose cyclic structure in your minor and require that it has to be a projected integral, what you find is that your supersymmetry has to be something like the 3-0. So this is not a 2, 0 in 6 dimension, this is a 3, 0. So this is just completely bizarre. But that's just to point out one thing. So, of course, the 3, 0 reflects the OSP 8/6. So so again, it's exact match with it. But then this 3, 0, what is this 3? So I'm recorded. Okay. I'm just gonna be crazy. So Chris Hall has so n equals 4 super real nails in 5 dimension lives to 2, 0 in 6 dimension. So Chris Hall showed that at least at the billion framework, you can show that the maximal supergravity in 5 dimension lives to 4, 0 in 6 dimension. So this was some recent interest that was generated by the 4, 0 theory in 6 dimensions. Now, if you think about ABJM, it's not maximal, so it's like n equals 6, which is a SUSY reduction of n equals 8. Then it's actually somewhat not surprising that if you use a Grassmanian, you only see a 3, 0 supersymmetry, which might be an embedding of the 4, 0. Right, so this is all I'm going to say because I think I've already done enough damage. How about that? Okay.
Any more questions?
So do you have any idea, well, let's say 6.2 loops, what sort of functions would appear?
Well, I think it's going to be, it's going to be transcendental 2. It's constrained by transcendental 2.
Okay,
so it's going to be
same.
transcendental 2 function.
Yeah.
Plus some weird functions that probably some descendant from these step functions.
And at 3 loops, do you have the same sort of non-analytic behavior?
3 loops?
At 3 loop 4 point, say? Do you know if there's this sort
No,
of
we haven't
non-analytic?
started looking. But obviously, at 4 point, we don't expect that because we don't see anything at 1 loop. So actually, so we expect that the first thing you see is at a 4 loop. And the 4 loop will actually, well, it's a 4 loop, but the 4 loop will help you fix for all that whether or not BDS is the answer for ABGM as well. But that will require a 4 loop computation.
Okay. Thanks. So let's thank
Okay.
you, Tin, again.
Well, thanks everyone.